Hey folks, we're going to do a little review of potential energy and kinetic energy and the total of those two and how they change, what are the circumstances, how do we tell when we have a lot of each type and a little of each type and when each type is changing. We did a little bit of this in class. This is more detail or in case you missed it. We're going to look at a ride that they have at Adventureland called the Space Shot, and we'll break down this video of people riding on the ride into little chunks and talk about the energy at each point in time. So let's watch the video first. Start at the beginning here. So they raise them up just a little bit. Got a little electric motor raising them up, and then there's these big pneumatic tubes that are going to launch them in just a minute. Now they're just kind of hanging out there. They're up a little bit higher than they started, but just hanging out still. Still hanging out. Oh, there they go. Way up high into the sky. And then all the way back down. And back up and down, and they oscillate a few times there. So you get the idea. Let's go back to the beginning. And then let's plan on making some graphs to track the energy of each type of energy over time. So let's make three graphs, three set of axes here. I'm going to do one for potential energy versus time, and we'll put that in seconds. I'll do one for kinetic energy, time in seconds again, and I'll do one down here for the total energy. Total of potential and kinetic energy, and we're just going to ignore any energy lost due to friction and air resistance. It's going to be pretty small compared to the huge amounts of energy we're dealing with the other types. So not a perfect approximation, but still a pretty good one, and makes it easier to do the graphs. So makes it better practice for us. Okay, I have this broken down into a few key moments that we're going to pay attention to. So we're going to have 11 seconds in. Something significant happens at 11 seconds. We'll show that on all three. There we go, 11 seconds. And then a significant change at 24 seconds. Just adding that about to scale, not paying super close attention to scale on this one. Just doing that a little bit. Okay, and then we got 28 seconds is the next one. 28. And then 32 seconds. That'll be where we stop. 32, 32. Okay, and we're going to keep track of each type of energy here, so we probably ought to just refresh our memory quick. What are we talking about with each one? Potential energy, we've got an equation for each of these, so that might be useful. Potential energy is equal to mass times gravity times height. Now, for the people riding on the Space Shot, mass and gravity will stay constant the whole way through. Doesn't actually launch you into space, so we don't have to worry about gravity changing. And the mass of the person stays the same because the number of atoms that make up their body stays the same. Height does change, though. They go way up high, they come back down low, way up high, come back down low. So potential energy graph, we're going to be thinking about height on that one. Kinetic energy, the equation for that is 1/2 mv squared. V is for speed, velocity. And so we're going to, again, note that mass doesn't change in this situation. Speed does, though, throughout. So we are going to pay attention to the speed when we're trying to graph kinetic energy on this one. And then the last one, total energy. If we had numbers for potential and kinetic energy, it'd be pretty straightforward just to add those together to get total energy. Instead, though, we're going to reference that really important rule about total energy, which says the total energy stays the same except when we have some external force or some external influence that's adding energy to our system or taking energy away from our system. And remember, since we're including potential energy, that's gravitational potential energy, we don't have to worry about gravity changing the energy of our system. That's just changing it from kinetic to potential. It doesn't affect the total energy. So let's go back to that video. We'll watch the first 11 seconds again, And this time we'll try and make a graph for what happens with potential energy, with kinetic energy, and with total energy during just that one phase. Back to the video, 11 seconds in. So right from the get-go, we have a little bit of motion up. They're going slowly up to a position where they can engage with the big pneumatic cylinder. This is what it's working out to right now. So we'll stop it right there at 11 seconds. So throughout that 11 seconds, we think potential energy. Again, we need to be thinking about height for potential energy. So all the way through that 11 seconds, they're moving up, right? They start down low and they get higher and higher gradually. So potential energy is increasing. You might notice there's a little bit of a stop in there, and then they get up high, and then there's a little tiny bit of a dip. Let's just attribute that to just a little shaking of the machine, though, and say that that isn't going to be something we need to include on our graph. So we'll just show an increase in potential energy over the first 11 seconds. And it looked like they basically started on the ground. So let's just put that at 0 initially, and then at some higher value at 11 seconds. But I also know they're going to go a lot higher after that, so I don't want to go too high. I want to save myself some vertical space on the graph. For kinetic energy, we need to be thinking with kinetic energy about the speed of that cart. And it looked pretty consistent. It wasn't going real fast, but it was pretty steadily moving up, right up until the 11-second mark. And that's where it reaches that height where the machinery can all engage there. And it's just going to stop at that position. So it's going slow, 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 slow. And then up here it stops. And we're going to see that continues for a little while. So kinetic energy, since it's staying at a constant speed, we'll have a constant kinetic energy. Since it's a slow speed, it'll be a low number for kinetic energy. So a low constant kinetic energy to begin with. And then just right at the end, we're going to drop down to 0 kinetic energy because it stops right at the end of that motion. As for total energy, well, we can see that the potential energy was increasing, kinetic energy was staying constant. So we know that total energy must be increasing. If we think through the situation, we've got this big cart that was at rest and down low. Now it's moving and it's up high. So it's got more energy than it used to. That energy must have come from somewhere. And it's good to think through where that comes from. That would be from the little electric motor, big electric motor that lifts it up to that position. Then we're going to have, in just a minute, more energy coming from the big pneumatic cylinders that engage with it. But for that first little bit here, we've pretty much got increasing energy the whole time. I didn't quite go to 11 there. I think probably at the very last moment, what we're going to see there is the kinetic energy of that upward motion converts into potential energy as that thing stops moving. So we get a little decrease in kinetic, a little increase in potential, probably about break even on total energy. So I'm just going to put that as flat. All right, next up, 11 to 24 seconds. Let's watch that part quick. 11 to 24, not a real eventful period. Just kind of sitting there. All right, 24 seconds. Whoops, jumped to the wrong spot there. Okay, at 24 seconds, that is, well, kind of boring, but we'll go ahead and plot it here. They haven't moved for that whole period, so potential energy is based on height. Height hasn't changed, so potential energy doesn't change either. Horizontal line there. Time keeps on ticking, but potential energy doesn't go up or go down. Kinetic energy, they're just stopped, so there's no kinetic energy for that whole period. We're at 0 that whole time. 0 all the way across. And total energy, well, potential isn't changing, kinetic isn't changing, so the total of those two also isn't changing. There we go. All right, now we've got more exciting stuff coming. Here we go. We'll do 4 more seconds up to 28. And there they go. All the way up to the top. And at the very top, it's important to notice here that they stop at the top. If they didn't stop at the top, they would keep going right beyond the top. So they're certainly glad that they stopped at the top. We need to pay attention to that for one of our energy graphs. Back to the graphs, potential energy goes with height. Well, they were down low and they got way, way up high. So potential energy is going to go way, way up high too. Potential energy has a big increase from 24 to 28 seconds. Kinetic energy is a little more complicated. So they were at rest down low here, and then they started moving upward, and they get going pretty fast there, but they also have to stop by the time they reach the very top. So they must have 0 speed here, 0 speed here, and then some fast speed in the middle. And so our graph needs to reflect that they would have 0 kinetic energy when they're down here, 0 kinetic energy up top here, but some large kinetic energy in the middle range there. So we're already starting at 0 kinetic energy. We need to get back to 0 at a time of 28 seconds. So we're looking at something like a big upside down V, or maybe a curve to it. Probably a curve is more accurate, but we're not going to worry too much about the shape at this point. So kinetic energy increases as it gets faster, but then it slows down, and stops, taking kinetic energy back down to 0. Last bit there, total energy. So this one is the trickiest of the three. There are 3 different stages here. Initially, it's given a push upward by these big pneumatic cylinders. And so if those cylinders weren't pushing on it, it would just stay still. If they were maintaining what they were doing, it would just stay at rest at that level that it was at before. But instead, those things push, making it go higher, so it gets more potential energy, making it go faster, so it gets more kinetic energy. Both potential and kinetic are increasing. So the total of those two is increasing as well. But that's just while that machine is pushing up on it. So that's just a small part of our 4-second time period there. So something like that, a big uptick. Then we have a little space there where the machine down at the bottom isn't pushing on it. And in fact, nothing is pushing on it. Just gravity trying to pull it back down, but gravity doesn't count for our external forces when we include potential energy. So during that time period, there's no external forces. And so that means that we aren't in the exception part of that rule. We're in the general part of the rule. The total energy doesn't change because there are no external forces. So we have a constant total energy there. And it's a little too big. Just a small section there. All this happens very quickly. Then at the very top, there's this device called an air spring. You could just think of it as a regular spring though. And as that machine gets closer and closer to it, that spring starts to compress, it squeezes, and so now it's pushing down on this car. It slows that car down faster than gravity does by itself. So now I need to think energy. If that machine, that air spring, is responsible for slowing down the car, it must be taking energy out of the system. The whole system, the car system, is losing energy as a result of that spring. So we have a little bit of a drop in energy down to 28, but notice that I didn't go all the way back down to this level. If I'd gone all the way down to that level, that would indicate we were at the same energy as we were before we lifted off at all. But that doesn't make sense here because while we are stopped again, we're way higher than we were at the 24-second mark. So 24 seconds, we're down here and stopped. 28 seconds, we're up here and stopped. Even though the kinetic energy is 0 for both, we have way more potential up top than we do down at the bottom. So more total energy still. All right. Next up, we've got from 28 to 32 seconds, and that's the trip back down. Let's take a look at that quick. Here it is. Falling, 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 and slowing down to a stop. All right. 28 to 32 seconds then. Let's take a look at that one. So potential energy goes with height. They start way up high, they end way down low. So we have a decrease in height, which means a decrease in potential energy. And it looks like it gets back down to around the same level as it was before it launched off. Maybe a little bit higher, but pretty close to the same level anyway. So something like that. For kinetic energy, we have sort of the same thing going on as we did before. When it was up high, it starts to fall faster and faster and faster. It was at rest, it was at a speed of 0. It gets faster and faster as it falls, and then it gets close to the bottom and something slows it down to a stop, so it gets back down to a speed of 0. So it starts at a speed of 0, ends at a speed of 0, which means it starts at 0 kinetic energy and ends at 0 kinetic energy. In between those, though, it has a fast speed at some point, which means it has a high kinetic energy at some point too. So we're going to have something that looks very much like what we saw earlier, something along those lines. Okay, last up, and then the high point there, that's somewhere in the middle of that time period. So that's just before the machine starts slowing it down again. Then on the total energy, at 28 seconds, the car is all the way up against the top, against that spring. That spring is compressed. So as it starts to move down, not only is gravity pulling it down, but that spring is pushing it down. So it gives it a little extra nudge. The thing falls faster than gravity would pull it by itself. So that spring then is making it move faster than it would without the spring, which means it's giving it some extra energy. So it took away a little energy, and then it's giving it right back. That energy is just stored in the spring. And as the spring stretches back out, it's not going to store that energy anymore. So that energy is going to bop right back up to this level here. Then we have the car falling. It's not touching the spring at the top. It's not touching the pneumatic tubes down at the bottom. It's just falling. Potential energy is turning into kinetic energy, but we don't have any outside influences that are changing the total energy. So we've got another little constant energy snippet there. And then it gets down to the bottom, and we have this pneumatic cylinder down at the bottom. It compresses and slows this thing down all the way to a stop again. And now we're back down to a low energy state because we're stopped, so no kinetic energy, and we're down low, so very little potential energy. And up here, we put that potential energy back at the same level that it was at before. So this one is back at the same level that it was back here. So with no kinetic energy, the total energy is just the potential again. So that's going to be back at what it was at 24 seconds. So something back like this. After this, the energy transformations just repeat again and again, so we don't need to go any further. All we would see there is that the range of movement decreases for the next few cycles, so all the energy graphs are just going to shrink a little bit so that we don't get to quite as high of energy levels for any of those three. So that is our total and potential and kinetic energy stuff. Review from class today and with some extra detail for you. So hopefully you found that useful. And by all means, let me know if you have additional questions on this, and we can work through a bit more of this before you take the reassessment. Thanks, everybody.